Howdy, y'all. Welcome back to my channel. I am Professor Parks, and this is my lecture series on the solar system. Before I get into too much, I want to say howdy to Clive and Judy, who are currently watching live. Today, we are going to talk about light, or at least this is the first lecture where I will start talking about light. Mainly its general properties and why it is so important to astronomical research or astronomical endeavors. So yeah, all right. Let's just jump right in, I guess. Boom, there we go. I like that. All right, so there will be points on here where I actually have to use my handy dandy whiteboard for the first time, which is nice. Because for some reason, the conversion between my PowerPoints and StreamYard doesn't like equations for some reason. Very much like my students, StreamYard doesn't like equations, which is just a shame, really. Howdy, George. Georg. Okay, I guess I'm sure I was pronouncing that way wrong. Howdy, Georg. All right. So, as I was saying, light. What is it? What is it good for? Well, what I can tell you is that if you're looking for a precise definition or a precise intuitive knowledge of what light is, I can't really give you that. What I can do is I can give you two basic descriptions of how we characterize light, how we use light. Because right now, as far as I'm aware, there is still very much of an open question as to what is the exact nature of light. As I'll go into later on, we can look at the light as either a particle, which is really kind of a misnomer, but we can look at the light in sort of a particle sort of way, or we can look at light in a wave as a wave function or a wave sort of way. And so neither of which is, shall we say, neither of which is a complete picture in my opinion, to be honest with you. So, but what is it good for? Well, as I may have mentioned before, astronomers have the disadvantage, I guess, of not being able to really physically manipulate the medium of their study. So when it comes to studying other planets, although that's becoming more of a possibility, but definitely when it comes to studying stars, when it comes to studying galaxies and the universe as a whole, there's no way for us to really get our hands, our grubby little mitts, on those things and really manipulate them in a lab setting. So the only way that we know, or about the only way we know to how to really gather any information about the universe around us, is through the collection and analysis of light. And so astronomers really have to be fairly clever as to how we go about doing this. How is it that we can essentially come up with different ways to get us answers to very fundamental questions like, how old is something? How far away is something? How much mass does something have? All of these questions can be answered through the analysis of light in one form or another. So, as I like to say, about 95% of all things that you're going to hear astronomers say, and yes, that is a completely made-up number, 95% of it comes from essentially that study of the light. The remaining 5% comes from lab, the little bit of things that we can actually reproduce in the lab, or essentially the underlying physics that allows us to make these, or the underlying physics that allows us to understand this light better. Like, for instance, taking solids, heating them up in the lab, finding out what they would do, seeing what kind of what the light emanating off of them how that would change based on the temperature of the object, things of that nature. Those sorts of experiments we can do in the lab, and then build off of that. Spectroscopy. That's a flat Earth joke for anyone not aware. Spectroscopy needs a container. Kind of. So, let's see here. There we go. So, features of light. Before we really get into features of light, what I want to start off with really is talking about the fact that there are 4 ways generally that I like to describe, or 4 ways generally that light interacts with matter. Light can be emitted from matter. For instance, the lights in this room, the sun in the sky, those are generating energy and emitting photons or emitting light waves throughout space. So emission is one. Absorption is another. So some light can be absorbed, for example. As we all know, the sun makes things hot. The reason why the sun makes things hot is because we and everything around us is absorbing a portion of the light that is coming from that sun. We also light can also refract or reflect off of an object. So, for instance, I guess this window is actually, I will come back to this window, but part of this window, if I look into this window, I can actually see my hand waving in front of it. And the reason why is because part of the light that's coming off, that's actually reflecting off my hand from the sun, is then reflecting off this light, window, and is then coming to my eye. So reflection and refraction, or the bending of light through a medium. So matter can either bounce the light off, or it can cause the light to travel in a different direction than it was initially. And then finally, you have essentially transmission. And so matter can be in some manner opaque to light. So this window, coming back to this window is primarily transparent. Most of the light that the sun streams in through gets to me. Part of the light is absorbed, and part of the light is reflected outward. So the universe might contain. That's a very interesting question. Fortunately, in this lecture series, I probably won't be getting it too far into that one. But yes, the universe having containment? Don't know. Oh, howdy, Reggie. Let's see. My thoughts, everything is a wave, quantum mechanics. If light is a wave, then it must have a medium. If it can't have a medium, too fast. My thoughts, everything is a wave, quantum mechanics. If light is a wave, then it must have a medium. You can't have a wave without something to wave. That you are not alone in having that thought. For a good portion of scientific history, that was the case. People did believe that that light was in fact not only a wave, but it required a medium to propagate. I will say that is not the current state of science. At the moment, our understanding of light indicates that a medium is not necessary for light to propagate from one place to another. And I'll get a little bit more into that as we move on. Oh, let's see. So, actually, let me do that then. Oh, nope, no, wrong one. How about that one? Aha. So, speaking of the nature of light, again, I cannot tell you exactly what light is. All I can do is give you descriptions of how we can analyze that light. How is it that we know that light interacts with matter? As a good old pragmatist, raised Midwesterner, I'm all about the pragmatism. So I'm really all about how can I describe things? How can I get something done with the information that I have. So the nature of light has been bandied about pretty much since the time of Newton. And as it happens, one of the largest sort of debates at the time was between Newton and Huygens, in that Huygens believed that light, as Rachie said, light was a wave. And Newton, on the other hand, believed that light was corpuscular, or essentially was comprised of small parcels of light. Now, as with the experiments of the day, for instance, the Young's double slit experiment, things like diffraction, these concepts or these experiments really could best be described with what light being or having a wave nature. Thinking of how particles interact with or interfere with each other to create interference patterns. It can be done, but it tends to give me a headache. It's far easier to look at interference patterns as if the light was in fact wave nature, and that pretty much was the case up until about Einstein, where it changed. Because Einstein, I don't know if any of you know this. Actually, Clive can't answer this because I know he knows this. So Einstein won the Nobel Prize. What was it that Einstein won the Nobel Prize for? Can anyone other than Clive let me know in the chat? But for now, we basically just kind of throw our hands up and say that light has both wave and particle properties. Really, it comes down to, again, pragmatism. How easy is it to, hey, Rach, you got it in one. Where is it? That one. Got it in one. So yes, the photoelectric effect. What Einstein showed was that essentially Planck had come along and proposed that light was in fact quantized. That light could only exist with discrete amounts of energy. And so Einstein showed that essentially, we're backing up a little bit. The photoelectric effect that Einstein illustrated was essentially that when light hits a medium, it's carrying a certain parcel of energy along with it, and once it smacks into that physical substrate, it's going to launch an electron off of that medium. Then you can construct equipment. Basically, CCD cameras work on this principle. You can basically put an electric potential across that and actually cause those electrons to move, hence creating a current. And so, and that is best described, I won't say only described, but best described as a particle. And so now we are, sorry, I'm a little bit fuzzy today, but now we are back to this idea of what exactly is light. Is it a particle? Is it a wave? Like I said, it really depends on what sort of applications you're what sort of applications you're interested in. If you're interested in things like the photoelectric effect, or if you're interested in things like how absorption spectra are created, then thinking of light as a particle is, I think, in my mind, is a far easier thing to do, or far easier thing to work with than trying to figure out how these things work if light were in fact a wave. But if I'm going to do the Young's double slit experiment, I'm definitely going to treat it as a wave as opposed to a particle. For the purposes of this lecture and kind of moving forward, I'm really going to, I'm going to start off by talking about it as a wave, because there are certain terms that we use which make sense only really if you think of it as a wave. For instance, wavelength. Thinking of trying to conceptualize what a wavelength is with relation to a particle, that can be a little bit counterintuitive. But let's look at a wave. So let's now basically put our the wave hat on and try to characterize what light is as a wave. So if we do this, then what we're saying is that light is a transverse wave, meaning that a transverse wave, as it propagates through matter or propagates through space, if there is any medium in the way, or if it propagates through a medium, it's going to cause the particles of that medium to go up and to go down. They're going to. It's basically going to cause those particles to oscillate up and down rather than backwards and forwards. So water waves are sort of the iconic depiction of a transverse wave, in our everyday life. If you look at if you see ripples on a pond, the leaf on the pond is going to bounce up and down as the ripples move through it. So the wave, as it propagates through, is going to have a certain speed, and it's going to be has a characteristic size or length, what we call wavelength, and that wavelength can be measured in a variety of different ways, so long as you're consistent. Typically, the wavelength is measured from peak, or the highest amplitude point, to the next highest amplitude point. That distance we refer to as the wavelength, or lambda. But you can do this, but again, if you're consistent, if you measure it from trough to trough, that's also the wavelength, and so forth. The other property that it has that is related to wavelength is frequency. Frequency is how often a particular point on a wave passes by a position in space. So again, if we look at the peaks of these waves, then we can see here that the upper curve, the purple curve, has a much shorter wavelength, and therefore also is going to oscillate things up and down more frequently within that 1 second, 1 second span, as opposed to the green curve, which is really going to only oscillate things once during that 1 second as the wave passes through it. And so for example, the idea of frequency is measured in hertz. Hertz being essentially an inverse second. So if something is 5 hertz, or rather, let's talk about TVs. You buy a TV, your frame rate or your refresh rate is going to be 120 hertz probably. And what that means is that every second, a new screen is created. In 1 second, 120 new screens are created on your television every second. So, here is one of the equations. This one's easy. So, speed of a wave. Yeah, I think you can see this. So, what we find is that unlike other transverse waves, like a water wave, light, Einstein tells us that light travels at a set speed, given a particular medium that it's traveling through, or potentially lack thereof. That speed is 3.8, or 3 times 10 to the 8th meters per second in a vacuum. And that speed c is equal to the frequency of that wave times the wavelength. So here we truly have an inverse relationship between the frequency of light and the wavelength of the light. So when we talk about light, if there is a mechanism by which the wavelength gets longer or larger, the frequency is going to drop commensurately. There you go. C equals lambda nu. Oh yeah. Well, I use F, or you can also use nu as well. I keep saying the caveat that I made is that the speed of light is constant through a particular medium. More specifically, it is. I like to think of it as constant through a particular index of refraction. And light can only slow down if the index of refraction is high, or goes higher. then the speed of light will actually decrease. So light travels slower through normal air than it does through space, very slightly. And light also travels even slower through water than it does through air. There's actually an entire field of physics whose sole goal is to see whether or not they can create a medium that will make light stop, that will actually do the whole Kylo Ren thing and actually cause light to freeze in space. I don't think we've quite got there yet, but they are trying. So I'm really going to hand wave this for now. Basically, that light, as we know it, the best definition of light as we know it is really an oscillation of electric and magnetic fields, and we think of these oscillations as electromagnetic waves. So refraction is essentially a measure. So the index of refraction is essentially a measure of how much a medium slows down light. I believe that is accurate. Yes, that is one way to define the index of refraction. So the properties of magnetic wave, like I said, this is the speed of light here again is not apparently doesn't even like numbers, numbers in scientific notation. The speed of light is 3 times 10 to the 8th meters per second. Like I said, electromagnetic waves do not need physical matter through which to travel through. There is, I pretty much said all of this. The amplitude of an electromagnetic wave is not distance, but the strength of the fields. In terms of sort of everyday parlance, the amplitude of a wave is its intensity. And really, I'm going to start referring to that as the brightness of an object or the luminosity of an object. And really, I'm going to be talking about that sort of thing somewhat independently of light specifically. What is the electromagnetic spectrum? Well, the electromagnetic spectrum is a fancy way of saying light. It is the spectrum it is looking at light as a spectrum of either wavelength or frequency or energy. And it encompasses, and essentially the electromagnetic spectrum is essentially infinite. There are no physical limitations to how low or how long a wavelength could be or how short a wavelength could be. There are certainly limitations to our technological ability to measure these waves, but essentially the entirety of the electromagnetic spectrum is infinite. What is it that makes the EM waves not need a medium when all of the waves we know do need a medium? Mark, that is an excellent question. I will have to look into that. I do not have a very good answer for you at this point for that. One thing I will say is that essentially, maybe Clive can. Gravitational waves don't need a medium either. My intuition tells me that the reason why is that most other waves that I'm thinking of at the moment basically require some kind of physical or a culmination of physical force, like sound wave is basically a pressure wave, whereas light, as I said, is the oscillation of the strengths of magnetic fields. So I think waves in fields do not need mediums. So I think the answer is there. I do apologize. I don't have a very good answer for that for your question, but that is an excellent question, which I am going to remember and look up and see if I can give you a better answer later on. So, like I said, the electromagnetic spectrum is infinite, but we have to manage it some way. When we look at the electromagnetic spectrum, we have to come up with some idea of what exactly are we looking at. And so we have devised basically 7 regions of light. The first one is the first one that I'll mention is the only one that is essentially biologically motivated, or the limitations of which are biologically motivated. And that is the visible part of the spectrum. It is by far the smallest region of the electromagnetic spectrum. And it is literally, pretty much literally defined as the bluest light that we can see, which for most people is around 400 nanometers. Nanometer is 1 billionth of a meter, so very tiny. And the largest, on the farthest red, is around 700, 750 nanometers, thereabouts. The other wavelength regimes have just been somewhat arbitrarily defined. And those go from, if we go from the longest wavelengths to the shortest, we have radio. Inside radio, you have Wi-Fi, you have FM, AM, you have also microwaves. Moving on from there, you get into infrared, then you get into visible, then you get into ultraviolet, then X-rays, and then gamma rays, and so forth. So that is the electromagnetic spectrum with decreasing wavelength. But if you remember, because light is constant, and the speed of a wave is the velocity of a wave is equal to the frequency of the wave times the wavelength. As the wavelength gets shorter, the frequency will go up. And so what we have is that so radio, for example, has very, very long frequencies, frequencies that are meters or meters in size, or even tens or 100 meters in size, or even longer. As I said, it pretty much goes infinitely outward. Radio waves also have the lowest frequencies, whereas gamma rays have tiny wavelengths, exceedingly small wavelengths, but incredibly high frequencies. And as I'll show later on, the frequency is essentially equivalent to the amount of energy that the light is traveling. If I were really going back to the beginning, if I were to be asked with a gun to my head, what exactly is light? To me, the nature of light is that it carries energy from point A to point B, and really nothing else. And in so doing, it communicates sort of the causal effect of the universe. So it carries energy from point A to point B, and that energy is characterized by the frequency of that light. Okay, well, say hi to Margaret for me. All right, let's see. Where was I going? Different kinds of electromagnetic waves. As I said, we as astronomers and physicists have broken up the electromagnetic spectrum into certain regions so that we can essentially have a better working understanding of what we're really doing. Because as I said, each of these particular regions basically spans a certain amount of range, and that energy corresponds to certain sort of physical phenomenon. So, for example, certain galaxies are studied in the radio because they want to know what essentially the hydrogen is doing. The hydrogen in these galaxies is extraordinarily cold, extraordinarily low temperature. And so if we can study in the radio, we can study this hydrogen in the radio galaxy and answer questions such as why that gas is what's the word I'm looking for? Why is the gas congregated in the way it is? Why does the form of the galaxy have the form that it does? How does the galaxy evolving over time? Things of that nature. Microwaves, we get into the cosmic microwave background. In the visible light tells us a lot about what the sun is doing in terms of what kind of elements there are in the surface of the sun, that sort of thing. And then gamma rays tell us about some of the most energetic phenomena in the universe, called gamma ray bursts and also supernovae. Visible light. Kind of going over that. Doppler effect. I'm going to actually table this for the next lecture. But briefly speaking, the Doppler effect is the apparent shifting of light or sound due to the motion of one object with relation to another. And we refer to these things as either blue shift or red shift. So if an object that is emitting a sound is coming at you, then the wavelengths of the wavelengths will get compressed, and the blue and the light will become bluer. Again, the wavelength gets shorter, the frequency goes up. If you look at the visible part of the spectrum, bluer has a higher frequency, and so it shifts the color of the light towards the bluer end of the spectrum. Conversely, if the emitting object is moving away from you, like the siren is moving away from you, then the wavelengths will get larger. It appears to be a redshift. Howdy, Blue and Alan. I don't think I've mentioned that. But yes, next time I will talk about I will go into the Doppler effect in more detail, because the Doppler effect is a crucial thing to understand, particularly if you want to look at things like how is it that we determine the distances to certain objects, and how is it that we find certain planets around other stars. Both of those require the use of the Doppler effect, or an understanding of an understanding of the principle of the Doppler effect, or really more specifically the principle of red shifting and blue shifting of light. Now, as I said, around the turn of the 1900s, we have Planck and Einstein, Niels Bohr, a whole bunch of really, really smart dudes. They basically came to the conclusion that light is quantized, that light, any kind of, if you were to basically cut light into a small component or a small piece, that piece would have a definitive energy. Does not have just some random range of energies. It has a very specific energy. And so it was postulated that light was not in fact a wave, but light was actually composed of particles of light called photons. Again, particle is somewhat of a misnomer. It's really not a hard object like this, but it does have particle-like nature, like the fact that it can actually push on stuff. And so the energy of any particular light is given by this really complicated equation. The energy of light, or the energy of a photon, is equal to Planck's constant times the frequency of that light. And that's it. So as I said before, the frequency of light is a direct indicator of how much energy there is. Planck's constant is, of course, a constant, which I don't know off the top of my head. That's why books are there. So, going back to talking about the refraction and or the ways that light interacts with matter. Now, to an astronomer, the most important ones are reflection, refraction, and dispersion. And the reason for that is because, as I'll talk about a little bit later on in another lecture, telescopes work on the principles of reflection and refraction. Reflection and refraction are essentially the tools, or the way that astronomers can take light and localize it so that it can be analyzed. Dispersion is the process of splitting light into its component parts, or splitting it such that we have a finer look, or we can see the individual wavelengths of light, or individual colors of light, as it were, better. We have a better angular resolution in terms of, I don't know if that's really the right way to go. I like to say that you take white light and you split it up into its components. The best example is, of course, the Dark Side of the Moon cover, where you have a prism, you have white light shown through the prism, and the fact that individual wavelengths, that the index or the refraction effect of light bending through a medium is wavelength dependent. So if I remember correctly, blue light refracts more than red light, and so you get so you have this dispersion pattern. So I said, yeah, I got that right. Hey, I'm on today. So yes, white light or blue light will refract more than red light does. And so this was the first time that a spectra was ever taken. And as far as we know, the first person to really do this was Isaac Newton. What Isaac Newton did was he took white light, basically from the sun. He set up a board which had a very thin slit, so that it was his way of narrowing down the light. That only the light through that small beam was allowed to pass through and actually enter into the prism. The rest of the light from the sun was blocked out. He wanted a more controlled way to look at the light. And so when he passed this collimated beam, or roughly collimated beam, into a prism, he noticed this dispersion effect, and he created this prism. This very simple experiment has been expounded upon many times to great effect. One of the first things that was noticed, or the first things that was discovered using this sort of method, was that the light that we see is not, in fact, all the light that there is. The infrared part of the spectrum was discovered when a scientist, and for the life of me, I've forgotten who it is specifically. I'm going to say Thomson, but I could be very wrong. When a scientist put a thermometer at one end of the spectrum, or at basically past the thermometer along the observed prism, he noticed that the temperature increased as it went to the right, and continued to increase as he moved off the visible part of the spectrum. And so he inferred that there was, in fact, actually more light there, more energy there, but it was just not energy that we could biologically see. So I'm going to, the last thing I'm going to be talking about today is types of spectrum. Spectrum, or spectroscopy rather, is the method via which scientists, physicists, astronomers, chemists will take this white light and will split it into its component parts. And they will create or look at what we call spectra. And there are three general types of spectrum. There is a continuous spectrum, there is an emission spectrum, and there is an absorption spectrum. Now, a continuous spectrum, a gentleman by the name of Kirchhoff came up with these rules. And what Kirchhoff tells us is that if you have a very hot, very dense object, be it a gas or be it a solid, that very dense, very hot object is going to put out light at all frequencies or all wavelengths. And so what you get is a rainbow pattern of color, essentially. The rainbow pattern is a good way of picturing it, but the astronomers like to use the graph, the intensity over wavelength, where we look at the brightness of the light as a function of color or wavelength. So a continuous spectrum, really hot, really dense. Now, if you take that light from a very hot, very dense source, and you pass it through a cooler, less dense medium, like a thinner cloud of gas, that gas cloud doesn't have to be cold by any stretch of the imagination. It just has to be cooler than than whatever is generating all of those photons that are coming into it. So, for example, the chromosphere acts like like this gas when we look at the sun. It actually creates the absorption that I'm going to be talking about. And the chromosphere has a average temperature of around 10,000 Kelvin. So it's certainly not cold, but it's far cooler than the billions of Kelvin of the environment that actually generated the photons that are coming out and passing through it. All of those photons, when they hit that gas, some of that gas is going to be absorbed, some of that light is going to be absorbed by the gas. And so on the back end, the observer is going to see the continuous spectrum that is from the white light source or from the hot, dense object. But they're also going to see dips, or they're going to see these black lines running through it, where some of the light corresponding to those very specific wavelengths, having those very specific energies, has been removed. The gas itself has essentially eaten that light. And so that is what we refer to as a dark line or absorption spectrum. And again, you can see from the graph of intensity over wavelength, you again have that overall pattern of that overall continuous spectrum, which astronomers like to call the continuum. And then superimposed on that, you get these dips. Not all of the light is taken away. Not all of the light is stolen out of the, is stolen by the gas. Only certain amounts of it are. And actually, that's very critical, which I'll explain in a moment. Now, let's imagine that you are an observer off to the side. So you are not looking at that 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 very hot, very dense object. You're looking at that gas cloud. So what's happening is that that light that is passing into that gas cloud and getting absorbed, well, light or energy cannot be created nor destroyed. And so that energy has to go somewhere. And what happens is that the energy that is absorbed by those atoms gets re-emitted to random directions. And so so that light comes coming out of that cloud in all other directions. And if we're off to the side such that we're not seeing the continuous source, we're not seeing the hot dense object, but we're only seeing the cloud, what we'll see is that missing light. We will see what we call a bright line or an emission spectrum, where here again, basically we have zero almost everywhere except for these bright kind of peaks where that light is being that was stolen from the earlier continuous source is now being re-emitted and sent into space. Like I said, this is Kirchhoff, just a summary of what I was talking about with Kirchhoff's laws. Spectroscopy. Spectroscopy is arguably the workhorse method of astronomy. I think it is, I guess, the biggest bang for your buck, as it were. I know of no other technique in astronomy that gives you quite so much information than can be extracted from a spectra. Things that you can pretty much immediately gather from from an astronomical spectra are the composition of the gases of that object. You can determine the temperature of that gas. You can determine the what we call the specific gravity of that gas, so you can get an idea of the mass, or the mass and or radius of that object. You can tell how fast it's spinning. You can tell how far away it is. The power of the spectrum is not to be ignored. It's not to be. I am losing my words. Oh my God. It is nothing to sneeze at. The spectrum is a very, very powerful tool in the astronomer's arsenal. Oh, I'm going to talk about Austin at the end of this lecture, because I'm going to ask for some advice actually from folks in the know. But like I said, that'll be after this lecture. When we talk about spectrum, or when we talk about the energy that comes off of an object, we can approximate it as if that object is a black body. A black body, by definition, thank you, not to be scoffed at. Thank you, appreciate that. A black body, simply put, is a theoretical material that re-emits all of the energy that it absorbed in the exact same way that it absorbed it. So energy in the visible goes in, energy in the visible comes out. That's basically what a black body is. So when we think of objects that glow in the night sky, or really any object with any kind of temperature in the universe, it's going to produce light like a black body, meaning that it's going to produce light over a span of wavelengths, of different wavelengths. Here I am showing you five different black body curves for 5 different particular objects. And what I mean by particular object, really what I mean is 5 things that are 5 objects of 5 differing temperatures. So here we have something that is 5,000 Kelvin. We have a star that is at 5,000 Kelvin. That curve that you see is how the energy is going to be emitted off of that object. A 4,000 Kelvin star, that curve, and so forth and so on. So what do I mean by how the energy is emitted off of it? Well, it's really just sort of accounting, in the sense that this curve, this tells you how much energy is being emitted as a function of wavelength. So here we can see that for a 5,000 Kelvin star, most of the light, if you were to catalog all of the photons that were coming off of that star in any given second, most of them would be in the greenish yellowy part of the spectrum. Some of them would be in the blue, some of them would be in the red, a whole lot of them would be in the infrared, where we couldn't see them, but most of them are going to be in the greenish yellowy area. That is the peak of the continuous spectrum. What I want you to notice is that there are essentially 2 consequences, or 2 properties of blackbody spectra with relation to temperature, that are very, very useful for astronomers, particularly if we want to know the temperature of something. The first one is the hotter an object, the more energy it emits. That seems pretty simple, seems pretty intuitive. But more specifically, the hotter an object, the more energy it emits at every particular wavelength. So if you were to compare the curves, the 5,000 Kelvin curve and the 4,000 Kelvin curve, and you were to go to any wavelength, the 5,000 Kelvin curve is going to be higher. It's going to be producing more energy at any particular wavelength. But also on top of that, the total energy of the curve is going to be higher. This is what we refer to as the area under this curve is, by definition, the luminosity. That is the amount of energy that is coming off of that object as a function of time per unit second. So, hotter the object, the more energy the object has or emits. The other one is the hotter an object, the bluer it is. Now we have and I think it's biologically motivated. We often think of blue as cold. As we get colder, our lips turn blue, what have you. And then also as red is hot. Essentially, if you get sunburn, your sun turns red, or your skin turns red. But from a physical standpoint, blue is actually hotter. So you can see this, particularly if you are a fan of blacksmiths, or welding by any stretch. You can see this with a welder's torch. When the welder's torch is turned on and the gas is at a low pressure, the flame is cooler. The flame is obviously not cold, but it's red and it's cooler than when the more gas is applied, and that flame goes from red to orange to white, and then finally to blue. So bluer is hotter in astronomy, and you can see that by looking at the peak of these wavelengths, or the peak of these curves that you see here. What we notice is that if you look at the peak of the 5,000 Kelvin curve, it is in the yellow. The peak of the 4,000 Kelvin curve is in the orange. The 3500 isn't even visible anymore. It peaks in the infrared. So you can see as this temperature goes down, this peak shifts to the right or shifts to redder or lower energy light. Commensurately, if we were to plot up a 6,000 Kelvin curve or a 7,000 Kelvin curve, that peak would move to the blue, to the point that a star that is 10,000 Kelvin, most of its light is not seen by the human eye. Most of the light, by far, most of the light is actually put out in the ultraviolet and, to a certain extent, the X-rays. That is a good question. And this leads me to another complaint about Neil deGrasse Tyson being a pedantic little twit. Neil likes to or has tweeted that that the sun is actually green, which, yeah, kind of. The surface of the sun has a temperature of 5,885. If you look at the wavelength, the peak wavelength for that temperature, it peaks in the green part of the spectrum. 555 nanometers, I think, is where it peaks. The reason why we don't see it as green, we see it as sort of a yellowy white, I think is simply biological. The way that there are cones or rods, I can never keep straight which one's which. For whatever reason, we don't have the light sort of resolution to really pick out green. Green seems always kind of just blur out and get confused with blue and yellow. So for the reason why we never see anything green hot, you'd actually have to ask a biologist about that. Well, if you want to know why grass is, if you ever have a child and you want to know if they ever ask, hey, why is the grass green? The grass is green because of our sun. Basically, the chlorophyll is a way of not only gaining energy from the sun's light, but also protecting the plant from getting burnt out. So the plant will essentially absorb all of the light coming from the star, or at least all of the visible light coming from the sun, except for the green part. Because the green part, there is just too many, oh, thank you, Mark, cones, color. I will not forget that now. Plants are green, generally speaking, because that is where the most energy is located, and they reflect that back, because that would essentially, if they absorbed all of that energy, presumably the cells would basically burn out. Neil deGrasse Tyson said, when you see a color, it absorbs all the colors except the colors you see. Yes, that I agree with him on that. So this blue shirt that I have, you see it as blue because it is absorbing all of the light coming at it except for the blue. The blue photons, when they hit this particular material, actually just reflect off of it. So yeah, the idea of color, the reason why we see color or experience color is because of different wavelengths being absorbed and different wavelengths being reflected. So there are two laws. This is for Clive. There are two equations which astronomers use to essentially codify those two relationships that I talked about. The first one is the Stefan-Boltzmann law, which is Stefan-Boltzmann law. The luminosity, or total energy per second coming off of an object or star, is equal to a constant, sigma, which is the Stefan-Boltzmann constant, times the temperature to the fourth power. So it's a very steep function, or it's a fairly steep function of temperature. So a slight change in an object's temperature is going to cause a significant change in the luminosity. And hopefully that you can see that by here, like the difference between the 2000 and the 3000 Kelvin curve, while it is dramatic, it's certainly not as dramatic as the difference between the 4000 and the 5000. So that is why the luminosity of something, the total energy that's coming off of something, is a function of the temperature raised to the fourth power. And then what's left is 4 pi r squared, which is the surface area of the black body. In this case, we're assuming that the black body is a sphere. So r is the radius. We will be coming back to this equation again, because what this equation is very handy in that, for example, if we want to know what the radius of a star is, if we want to know how big a star is, then we need to basically come up with a way to determine two things. We need to come up with an independent way of determining the luminosity and its temperature. And if we can do that, then we can make an estimate. Astronomers can figure out just how big things are. Or if somebody wants to know how hot something is, you can make an independent measure of its luminosity and then figure out a way of directly measuring its radius, and then you can get its temperature, or any combination thereof of all of these things. So that is the Stefan-Boltzmann law. The next one is the Wien's law, which is also very simple. And I'm pretty sure I am going to get this wrong. Actually, you know what? I'm just gonna put K. Because I can't remember the exact numerical constant. It really depends on the units anyway. Wien's law is that the peak wavelength of a black body is equal to some constant, which depends on the units that you're using. So angstroms, nanometers, Kelvin, Celsius, Fahrenheit, whichever. Depending on the units you use, this constant's going to change. But essentially, it's the peak wavelength is equal to some constant divided by temperature, just an inverse function of temperature. So if the temperature goes up, this will go down, which means that temperature goes up, frequency or wavelength goes down, light becomes bluer. So that's how we codify that message. Oh, Nimrod. Wien's law, basically just summarizing what I've said. And stars, like I said, radiate as, to first order, stars radiate as black body. It gets a little bit more complicated than that, because essentially, because a star has many different essentially layers to it, some of the light will actually get trapped and then re-emitted in other parts of the spectrum, what we call something called line blanketing, but that's beyond the scope of this course. But to first order, any object with a temperature can be treated as a black body. And at this point, I am going to stop, and I am going to all right, let me see if I can decode this. dN is proportional to p squared dp over, that looks like Planck's equation, Planck law. But weird. All right, I'll figure that out later. So, what you're trying to tell me there later. So, basically, this is where I'm going to end the lecture, because I have to meet with a professor in about 15 minutes. And also, the next part of this, I think, is vitally important to know, and I want to go through it I don't want to. I don't want to tack it on at the end of a lecture. I don't want to go through it quickly because I'm trying to finish up. And what that is we're going to be talking about the internal structure of atoms and how the changes in those internal structures when we're going to talk about the internal structures of an atom, and we're going to talk about how that internal structure changes when light gets brought into the mix, specifically the movement of electrons, because that in turn is going to talk about how we actually, what is it that actually produces the spectra that we see, either an emission spectrum or an absorption spectrum, and how is it that I can use that information to come up with the composition of the gases that are in the star, how fast it's moving, things of that nature. So so the next lecture is that I'm going to talk. The next lecture is going to be addressing that topic specifically. All right. Yeah, it's Planck's law. Okay. I'm not used to seeing it in that form. Yeah. All right. Not used to seeing it in that form. So all right. So and that ends the lecture for today. I hope you all found that informative, entertaining. Definitely hope you found it entertaining, and hopefully at least a little bit informative. So like I said, next time we'll be talking about basically the Bohr model or structure of an atom, Bohr model of the atom, that sort of thing. If you like this sort of content, please like, share, and subscribe. If you'd like to help me out in my efforts for outreach, please consider becoming one of my patrons. All the proceeds go to basically bringing astronomy to areas that don't have the resources don't have the resources to look through telescopes, don't have the resources to experience a planetarium show, that sort of thing. So, but before I go, what I kind of want to just throw out there, and maybe folks in the comments can share their thoughts, and people who watch this later maybe can give me feedback in the comment section, is that so there's a flat earther by the name of Dan the Waterman, and I spoke with him on a live stream yesterday or so, and he is keen on getting me to having a conversation with Austin Whitsitt. And I was in the process of basically hammering out when I was going to appear on his stream, but that got derailed because apparently someone in the Discord channel was really ranting at him, telling him that he hated him. So obviously he thought that deserved more of his attention. So we never really finalized that. So what I'm kind of getting to is I told him that I would do it. I'm not backing out. I'm just a little worried about how it's going to be treated or used in the future. Really what I want to do is I want to have a conversation with the man. I want to try to find out where he's coming from, why it is he has the views that he does, why he thinks that astronomy has essentially been debunked, why relativity apparently has been debunked. I'm not entirely certain about that, how that happened. But the issue comes into, or the thing that I'm afraid of, is he's going to bring up some very valid points. Cosmology has some problems. Our understanding of the nature of the universe has some open questions. And as I said in a previous stream, I actually have to eat some crow because I've been telling people that this axis of evil thing in cosmology isn't a thing, and apparently, actually it is. So I actually eventually found a scientific paper describing what the axis of evil actually is in the cosmic microwave background and explanations as to what it could be. But for right now, there is an anisotropy in the cosmic microwave background, which is aligned with the plane of the solar system and seems to be in line with the movement of the sun through the universe. What that would indicate is that the cosmic microwave background, or what that would indicate is that we have a preferential place in the universe, that the universe reacted to our existence before we even got here, which is a little weird. So, and I don't have a good answer for him on that. I can tell him what this paper tells me, which is that there are any number of reasons why this anomaly exists, and really, it's a really, really small anomaly. It's real as far as we can tell, but it is small, and so there are, like I said, there are a number of reasons. But anyway, I'm kind of rambling at this point. What I'm concerned about is I don't want to look like an idiot. Is really what it boils down to. And I'm also worried about my own motivations for why I want to have a conversation with him, because I have to admit that, I'm hoping that having a conversation with him, I can attract obviously more subs, more viewers. I don't like the way that makes me feel to realize I'm being selfish in that way, but that's where it is. So I don't know. I'm just, like I said, I'm just worried and just wondering, just basically on a scale from, no, I'm going to be nice. How bad of an idea do you folks think this is? I'm not going to, I've already told them that I do it. I'm not going to back out from it. But cosmology does have open questions, which I know, or I have seen other folk. Well, no, I know from debates that he's had or discussions that he's had with, say, McToon, he basically latches onto the fact that we can't perfectly describe the universe, and he uses that to essentially say that the entire field of cosmology is bunk, that essentially the Big Bang Theory has been debunked because it does not have answers. So yeah. Yeah, I don't know. I'm hoping, because it's not going to be strictly a debate, or at least it shouldn't be strictly as a debate. I'm hoping that his auctioneer type voice or delivery will be a little bit minimized. Oops. Yeah. I don't know. He seems to be getting. I appreciate you putting that out there, Mark. Thank you. And all right, fair enough. The reason why I want to have this conversation with Witsit, if I want to be more sort of from an altruistic bent, is that, this is probably a selection bias, but recently he seems to be getting a lot of attention. He seems to be and particularly he seems to be dredging up or bringing back this idea of the electric universe that originated, I think, with Ken Wheeler, which is honestly garbage. And I don't like it because it's intelligent enough sounding that people are really latching onto it. Not that, folks who believe that the earth is flat need a reason to latch onto something, but that he makes it sound conceivable. And I think that really, really needs to be challenged. And I think it needs to be a challenge in a way that isn't as confrontational as, say, a debate format. More of a conversation. So yeah. I don't know. Thank you, Rachie. I appreciate that. Appreciate you saying that. Why give him even more attention? Yeah, I thought about that as well. Um, I think that I think that how should I put this? He's getting attention, and I don't think it's one of these things where his ideas need to be challenged. Because the growth that I've seen, again, this could very well be a selection bias that I'm looking in just the places that I'm looking, I'm seeing this, and I'm just not seeing the entirety of, say, the flat Earth community. But it's a lot of I see a lot of traction with what he has been saying among the flat Earth community. A lot of people are buying into what he has to say concerning the electric universe and the semi-luminous ether and all of this. And I want to basically be able to help set the record straight on that. Because, yeah, the semi-luminous ether is not a thing. I hate to say this, Reggie, but no, science tells us that we have done experiments that do not seem to indicate that a semi-luminous ether or any kind of medium exists in space. Actually, it would violate its kind of relativity is kind of prohibitive on that idea that there is, in fact, a medium. Because if you have a medium, the implication there is that you can then have an absolute frame of reference from which to measure the motions of all things, which again, relativity tells us is not possible. Yeah, I noticed that he's been promoting me quite a bit, which, like I said, part of me is like, yay, I get more notoriety, woo! But I also, I wonder about the motives that Dad might have as well. And again, I kind of feel icky for being happy that he's promoting me. But the truth is, you won't change anyone's mind by debating him. Not a single one. I don't know. Will I not change anyone's mind? Maybe I might. Maybe not. But I might be able to sow doubt. I might be able to intelligently sow doubt in the minds of other people, and I can also provide explanations that others who are watching, who are not flat Earth, they will. Hopefully, I can explain why it is that relativity has not been debunked, why it is that cosmology tells us that we live in an expanding universe where a dark matter exists and dark energy probably exists. If I can educate people on that, then maybe others can use that to combat misinformation in other places, other discords or what have you. Because ultimately, my goal is education. My goal is to be an educator. I want to bring people. I want to bring astronomy to the masses. I want to bring our current understanding of the universe to folks, and to basically set this record straight, and try to do so in an honest and genuine way. So, who knows? Yeah, I've picked up on that as well, Meraki. Oh God, Wheeler. Yeah, Ken Wheeler. Before I go, I will, because he's a friend of mine and his videos are absolutely amazing. If you have not watched AB Science's response to Ken Wheeler's series on the electric universe, it is a must watch. He just rips Ken Wheeler to shreds. Basically exposes that Ken Wheeler has no idea what he is talking about. That it is truly word salad. That there is nothing coherent about what he has to say. And that a lot of what he claims, particularly in the context of ferrocells, is just wrong, to the point that it's probably a lie. It's not that he's just wrong. He has to be. He is so wrong that he has to be lying. He has to be deceiving. So, AB Science. If you haven't checked out his channel, find his channel. You won't be disappointed. He's a very dry sense of humor. Very, very intelligent guy, and I think he does. It's a little bit more rigorous than, say, your average debunker. He does go into the math, which I think is a good thing. Yeah, I would highly recommend his stuff if you've not seen it. So, no, AB who's changed his name to what is it? Iron, cobalt, nickel. He just recently got his PhD. So I think he's in his postdoc. What was he calling himself now? Iron, cobalt, nickel. He just recently got his PhD, and I think he's in his postdoc. He moved, so he's got a lot on his plate. He did say that he's thinking about coming back to the tubes, but right now life is other things in life are his priorities. So, Ken Wheeler has a book. Yeah, Ken Wheeler has a book. Jesus, wow. I don't know what to say about that. I don't know if I could imagine even trying to read that. Holy shoot! And thank you, Raichi, for putting the channel link in the description. Yeah, see, iron, cobalt, nickel. His thing is magnetism. He is an expert in magnetism, which is probably why he did that, or why he changed his name. So, but again, thank you all for watching. Thank you all for being here. Thank you all for your support. I have no words for it, although apparently I have no words lately at all. So, but yeah, thank you all for your support. Particularly, I put that video out about my health, and the comments. Yeah, I don't have the words for it. So, thank you all for your support, and thank you for watching these videos. And yeah, so I have to go meet with a professor about actually possibly creating a class about the philosophy of science, or at least the history of science. So, or a history of scientific revolution. So, hopefully that goes well. And if it does, or even if it doesn't, I may just decide to make lecture videos on that anyway. Even if I can't get it as a class approved by the university, I may create lectures and put them on the tubes for giggles anyway. So, all right. Peace out, everyone. Clear skies.